Okay, the time is now 3:05. Time for our next presentation by Zeve Akerling from the Aerospace Corporation. He'll be talking to us about ROESA, getting your autonomous software agents to talk to each other. Zev.
Hey everyone, I'm Zeve Akerling. I hope you all can hear me. As mentioned, I'm here from Aerospace, and I am here today to talk about ROSA, a project that a number of us at Aerospace have been working on. Before I get into what ROSA is, next slide. Let me say a little bit about why we're doing this. First of all, in my opinion, getting sophisticated autonomous agents to talk to each other is going to be hard for the same reason that getting any two sophisticated complex pieces of software to talk to each other is hard. And that in turn is because getting the people who develop these systems to talk to each other is hard. Even if your documentation is very, very good, and as we all know, that isn't always the case, uh, the map is never the territory. An ICD or the like is never going to be a perfect representation of a complex real-world software system. And so there's always going to be communications friction. Oh, we forgot to tell you about X, tossing stuff back and forth over the fence. It's bad enough with other organizations in your local group, worse with teams in another subdivision, and with external teams, of course, it can be excruciating. And again, in my opinion, autonomous software is likely to actually make this worse. First of all, we're just asking more sophisticated capabilities from these systems, so they're going to be intrinsically more complex. There's going to be more stuff that you, the software developer, need to keep track of, more ways that these systems can be doing something other than you expect. On top of that, you look at the interfaces, and these autonomous systems are going to be interacting with each other, us, and the world in fundamentally new ways. And that means fundamentally new ways for things to go wrong. So if you believe this argument, basically everything is terrible. However, the way things are going, we're going to need more autonomy to perform the missions we want to do. So you need to do something. And ROSA, the resource-oriented embedded system architecture, is one exploration of things you can do. So starting out with ROSA, we first looked around to see how other industries besides space were grappling with some of these issues of software complexity management, integration management. And looking around, we saw that a really good system to try to emulate, next slide, is actually the web itself and its latest incarnation in the cloud. So if you look at the web, you have tens of thousands, hundreds of thousands of information systems all interacting with each other, and usually developed by organizations that have never talked to each other once. Somehow this works well enough to support billions of dollars of financial transactions and basically our entire civilization's information flow on a good day. If you pop the hood on why this actually works, it turns out to be due to a set of architectural principles called REST, representational state transfer, that guide but crucially do not specify the behavior of information systems on the web and cloud. These architectural principles include the client-server architecture, communications, session statelessness, uniform interfaces, and several others. We could talk about REST design philosophy all day, but for now, I'll say that people have generally been pretty happy with the sort of soft power guidance REST is provided on the web. And increasingly, people have looked at applying RESTful architectural principles to constrained embedded systems. Next slide. And personally, this is where I think this gets interesting for the space domain, because this application of REST to embedded systems, which many of us know as the Internet of Things, does have some overlap. In both cases, you're trying to target agile integration of very compute and power constrained embedded systems, and you're trying to get increasingly a large number of them to talk to each other. So within the Internet of Things, a very powerful and popular protocol is Coapp, the Constrained Application Protocol, which is to IoT as HTTP is to the web. Like HTTP, it supports RESTful APIs. It has a client-server request-response model. But unlike HTTP, it uses very low latency UDP packets and generally has very little protocol or wire overhead to it. So it's nice and neat. So we thought this was pretty neat, and we decided to investigate Coapp for space problem domain. And we chose to make this concrete by applying it to some small sat flight hardware we had available from Aerospace's internal small sat program, AeroCube. Next slide. So what we did here was take some AeroCube IMUs and reaction wheels and hook them up to a dev kit standing in for a higher performance compute element, essentially a flight computer. That flight computer was hosting a Coapp server, which exposed a REST API, which represents these resources, IMUs, reaction wheels, the like, as URLs, universal resource locators, the exact same sort of thing that you would type into a web browser. And in fact, with this, we are now able to literally browse the spacecraft using URLs to read off IMU acceleration values, issue reaction wheel commands, and the like. Now that may sound kind of cute and gimmicky, but if so, I would urge you to look again. I started out by saying that if you use a RESTful approach to representing physical spacecraft resources, other kinds of resources, that may give you some nice capabilities. And look here, we've already made the spacecraft so RESTful that we can literally browse it in Chrome using a open source off-the-shelf plugin called Cooperative. So there's maybe some advantages that you get as a human developer for doing this right off the bat. First of all, if somebody hands you a payload board, subsystem, anything else running a Coapp server like this, and with an Ethernet interface, you can plug that into a workstation, fire up Chrome, and you can be immediately interacting with the system, seeing what resources it has available. And that can be, again, in a web-like fashion, serving you human comprehensible information on how it wants to be used, resources available, data types, the like. And so you might be able to serve live information that we're used to getting offline in an ICD. So essentially, the developer from some other team may be able to comment the interfaces for this system, much as we already expect people to comment the implementation code. So of course, this isn't a magic bullet, but you can see that this might help expose implicit tribal knowledge and reduce communication friction between separate organizations. Next slide. So that's all very nice, but we did say this talk would be about getting your autonomous software agents to talk to each other. So we decided to look at one particular aspect of autonomy, resource negotiation between autonomous agents. Just like any human enterprise, we expect that cooperative autonomous operations are going to be resource constrained. You have limited time, two physical systems can't occupy the same space, you have limited communications bandwidth, power, etc. So we asked ourselves, how could a REST architecture help support these kinds of cooperative autonomous operations? And it turns out that it may help for many of the same reasons that it could help a human developer to interact with these systems through a RESTful API. Next slide. And this turns out to be due to another REST architectural principle called HATOAS, hypertext as the engine of application state. It's a terrible acronym, but a very powerful concept. So this basically boils down to hyperlinks, again, like you would see on any web page. So, you go to your favorite portal site, you want financial information, you see a hyperlink that says finance, and if you click on that, it's probably going to take you to the information that you want. It turns out that we can do machine-to-machine communication the same way and use hyperlinks to allow one information system to programmatically and automatically navigate through another one. But there we call that schemas. Additionally, these schemas, which can do low-level organization of information, can be used to show relations between high-level concepts in things like ontologies and knowledge graphs, which can be used for high-level rules-based decision-making for autonomous systems. An example of this we see every day is actually Google Knowledge Graph. That's the box that you see to the right of many of your web searches. The bottom line in all this is that you can imagine that the same schema, which can make navigation of information system by another more hands-off and automated, could perhaps seamlessly flow up into high-level concept representation for autonomous decision-making. Next slide. So we wanted to do an actual concrete demo which would show this. And what we came up with was using two very simple Python scripts representing more sophisticated autonomous agents using rules-based or statistical inference-based learning. So in this demo, you have two agents running on two separate small sats. Each agent has a mission to perform, but to perform their missions, these two agents are going to need to contend for a single physical resource on one small sat in this case, a reaction wheel. So in this scenario, Agent 1 enters a mission region, and it does a Coapp request to a Coapp server to acquire control of this reaction wheel resource. Later on, Agent 2 enters the same mission region, and it'll attempt to do a Coapp request to gain control of that same reaction wheel, but it's going to get blocked. Agent 1 already owns it. However, Agent 2 will get provided with the URL for Agent 1, so now Agent 2 knows who to talk to and exactly where to go to negotiate for access to this reaction wheel. So Agent 2 and Agent 1 are basically now going to arm wrestle for control of this device, and it turns out Agent 2 has higher priority. It gets control of the wheel from Agent 1. Next slide. So this is pretty neat. Again, these were just very simple Python scripts doing Coapp transactions, standing in for more sophisticated agents. But here we showed that these agents were negotiating for a system, a physical resource that was uniquely identified by a URL. So negotiation takes place in a framework where URLs identify the resources and also identify the agents to each other. And these are not just abstract labels. The URLs allow you to reach out and find who you want to talk to out on the network. Also, because this is leveraging off-the-shelf open source commercial technologies, we had easy access to DTLS for encryption authentication. And of course, there's all sorts of stuff you can do for permission schemes on top of that. Next slide. So that was a nice, simple little demo, but we wanted to take this to a more sophisticated and demanding use case. And so we went to Hive. Some of you may have seen Dr. Henry Helvagian's previous presentations here at the workshop on the Hive concept. Hive is using many smaller small sats, which self-assemble to create larger structures, thereby enabling mission capability that it would be harder or impossible to obtain by different methods. Of course, if you're trying to do this kind of self-assembly and coordination, you're going to run into many demanding challenges for autonomous interaction between autonomous agents. And so we thought that ROESA could be both useful for Hive and that this would be a really great proving ground to test out the technology. So in this scenario, you have a dish array self-assembled from 19 small sats that dock together and fold up kind of like origami into the final structure that you want. During this folding process and when it's assembled, you need to coordinate each small sat's reaction wheel commands to keep this structure stable and doing what you want. And so now you not only need attitude control, you need distributed attitude control. Next slide, please. So now you have attitude control instances running on each of 19 spacecraft flight computers. And these need to keep track of both local state and exchange state information with other vehicles in the aggregate. Next slide. So we tested this concept using ROESA Coapp communication to do this distributed attitude control with a software loop simulation. But now, of course, we're not doing software loop for a single software process on a single flight computer. Now we're simulating software processes running across 19 flight computers. And so those software processes are interacting with a dynamics model, which is performing kinematic flexible multi-body dynamic simulation of this whole assembled structure. And so we can use this to look at things like control bandwidth, communications latency requirements. You know, what would you actually need to do to actually make this happen? And is something like ROESA a good solution for doing that? Next slide. So I've talked a lot about agents through this discussion. So let me say very quickly like what that means in nitty gritty. So again, Coapp is a client-server request response protocol. And so what we're doing is we can support two-way agent communications across multiple agents, just building that out of one-way client-server interactions. Next slide. So in the actual simulation framework, you have a single dynamics model simulation, or actually now a dynamic server with a Coapp server built into it. And you have multiple flight software processes or software agents, each implementing this distributed attitude control algorithm. And these agents are now interacting with each other in the dynamics model through Coapp requests. And then you're again using Coapp to synchronize synchronize interaction between the various components of the simulation. So in this diagram, we have 2 of these agents represented. Of course, the full sim has 19, and really we could scale up to 200, 1,000. We're leveraging the built-in scalability of REST architecture that the web uses. So we're really only limited by how much computational horsepower we have and how fast we can run if you're interested in real time or basically getting a result in a timely fashion. Also note that we're using Coapp and ROESA to support the flight-like interaction between the software agents that need to perform the mission, but we're also using it to support the simulation framework itself, because the RESTful Coapp protocol is well suited to the scalability problems intrinsic in both the flight architecture and the simulation framework that's needed to support modeling of this more complex system. Next slide. So simulations and lab demos are all super great, but now I would like to move over to talking about a demonstration of this idea that we're trying to do on orbit. And for that, we're collaborating with another project here at Aerospace called Vertigo, where Vertigo is a payload on the Slingshot mission that Kevin Bell mentioned at the previous keynote discussion. And so Vertigo is demonstrating on-orbit automated attitude control system identification. And at a very primitive level, this is very much like if you ever see anybody sort of rattle a present, a gift wrapped present back and forth to try to guess what's inside. That's what you're doing here, except instead of a present, you're using the reaction wheels on a spacecraft to rattle the vehicle back and forth, and you're looking at the response from the IMUs to see the response and the structural modes of the vehicle. So Vertigo is looking at taking the system identification process and automating it to a greater extent. And so they're doing this on a fairly standard embedded processor. And so we were looking at using these RESTful technologies to add some value for an extended mission, where instead of running the SysID algorithm on that fairly constrained embedded processor, we can now run the SysID algorithm on a more powerful Kubernetes managed compute node. And that higher performance processor is able to interact with our embedded processor using a RESTful Coapp protocol. Next slide, please. So the way this looks in detail is you have this high performance processor where the computationally intensive system identification algorithm is now running. That is actually running in a Docker container managed by Kubernetes. And that is now enabled with a Coapp client, which is letting you reach out to a, again, compute constrained embedded server with a Coapp server in it. So this isn't full agent autonomy here. This is a pretty straightforward client server interaction, but this does get you some interesting things. So you have this embedded server, which knows how to talk to reaction wheels. It knows how to talk to IMUs. And it's interacting with this very sophisticated software stack involving Docker and Kubernetes, but all of that complexity is abstracted away from your small embedded processor. All it knows is that a Coapp request comes in and it serves that Coapp request, and a client is a client is a client. Meanwhile, on the side of the high performance processor, this very compute constrained embedded processor has now become a first-class citizen in this more sophisticated cloud-like Kubernetes Docker environment. And the physical system resources that embedded processor exposes, again, things like IMUs and reaction wheels, are now available through URLs. And so that fits very nicely with this more cloud-like model. So I have to stop a little bit abruptly here. I've been trying to fit a lot of material into this time slot. I hope I've given some examples of how you might be able to use these RESTful approaches to manage software complexity, integration, and to start to approach perhaps some collaborative autonomous type problems. I would like to thank the many, many people who have joined us in working on this, both the direct ROESA team and our collaborators and the PIs for projects like Hive, Vertigo, and the Kubernetes Docker work. And I would also like to thank everybody here for your time today.
All right, excellent. We have a few questions in the Q&A. First one from Peter Fiddleman. Have you looked at redundancy and reliability concerns in the Coapp based systems you've tested? Are they intrinsically more or less robust to failures than a traditional approach?
So with respect to traditional approach, you're now looking for more system level reliability, I would say. So you're looking at using this in systems where if something goes out, you have a hot spare or backup that would come up. I would say more specifically with respect to something like TCP/IP, remember you are using UDP packets, which do not intrinsically have quality of service guarantees. So you'd be looking at building quality of service for delivery at the application level, which Coapp provides for. And so it's up to you to dial in that quality of service guarantee versus the increased amount of latency that you can live with.
All right, great. Next question from Caleb Royer. Are there any guarantees, assumptions you make about timing, and what type of systems where these concepts, where this concept works or fails? UDP is non-guaranteed delivery, nor any guaranteed timing.
That's correct. And as similar to the previous question, you need to build your own guarantees for quality of service on top at the application level. And in terms of hard latency, that's difficult to give a single number to because something like UDP is generally running over Ethernet. And so the physical timing margins are going to depend on your physical hardware implementation. But I would say is that UDP and Coapp is on the low end of the spectrum of the latency, low-level latency that can be supported by protocols that at the same time give you advantages of these RESTful design architectures and some of the benefits that come with those.
Okay, great. And we have one more question from Chris Knight. Curious on your thoughts on HTTP3 and impacts to RESTful communications with space systems.
Sorry, I'm not very particularly specifically familiar with HTTP3, so I can't say much about the cost-benefit analysis for space applications there.
All right, so we'll give another moment to see if any other questions trickle in. All right, thanks a lot, Zeve. Excellent presentation. And of course, if folks do have any other follow-on questions that they haven't thought of yet, they can be taken over to Slack and you can address your question to Zeve